So, last class we had started talking about absorption spectroscopy, right, and we where I think we ended the class by showing you this that cell where you have this wall and all those things, right. So, let us look at that again. So, this was the absorption spectrum of amino acids, that is what we were talking about. So, on the y axis you have the extinction coefficient that is plotted against the wavelength, right. Okay. So, this is what we were talking about, and what we said was that based on your absorbance, which is this one A lambda absorbance, this is equal to log of I 0 by I, which is equal to epsilon times C times L, right. Now, but this I 0 and I, they are a little bit different in the sense that I 0 is the intensity of light which is striking the sample solution, right, not the cuvette. I is the intensity which is coming out of the, or which is being transmitted by the sample solution, right. So, that means before it leaves the cuvette. So, what I mean is, as I was saying, so if this is a zoomed in portion of your cuvette, so if this is your sample cuvette and you have zoomed into a portion of the sample cuvette, right. So, here you see this is your thickness, this is your cuvette wall thickness. Okay. Now, when we talk about the path length, that path length essentially should not be including the cuvette wall, right. Why? Because that cuvette wall does not give rise to anything, it is nothing there. So, the path length should essentially be that path length throughout which you have the solution. That is why you see the L varies from where, or the L ranges from where, the L ranges from, or the L is within the inner walls of the cuvette. Okay. That is essentially what the L is, right. But then when you stick your cuvette in an absorption spectrometer, okay, when you stick it there, you have to have the walls, right. And because of this, the incident light, which is this one, this is the incident light, where is this light coming from? This light is coming from the lamps we discussed yesterday. This incident light II is the one which is striking the outer wall, but by the time it reaches the sample solution at the inner wall, it is not necessary that II is to be equal to I 0. There can be some scattering, there can be some other extraneous absorptions and all these things, and hence typically what always happens is I 0 is less than I of I, the incident light. So, the same thing happens on the other side, the IS, which is the one which leaves the sample or leaves the cuvette, is not the same as I, which is the one which is coming out of the sample, right. So, how do you take these things into consideration? I mean, how do you make adjustments for this, or how do you correct for this? So, what people have devised is, people have devised something known as a double beam spectrophotometer, okay, double beam. So, in double beam what it refers to is means two beams, right, essentially double beam. Okay. So, what they do is, you can see you have the source, this is the source, the lamps you have, then you have a monochromator, because I showed you that the lamps have these series of wavelengths, right. So, this series of wavelengths, and the monochromator what it does is it selects the wavelengths for you, it disposes it and then it selects the wavelengths for you, right. And then after the light is coming out of that, after dispersion, then you have a beam splitter. You see this is known as a beam splitter. So, beam splitter means what it sounds, beam splitter means it splits the beam, that is it. So, you have a mirror like this, okay. So, you essentially have a mirror like this, right, which would pass one half like this and the other half comes to the other side, okay. So, that is why you will see it is a combination of two, there is one which goes in this direction, the other one which comes in this direction. So, one gets reflected to the left, the other one gets reflected to the right, okay. So, now you started with one beam coming out of the monochromator, you have split it into two. So, that is why it is called a double beam spectrophotometer, okay. Now, what is the use of this? Now, think about this. So, suppose in this one, say in this one where IS, S stands for your sample, okay, and here when we are talking about this one is IR, where R is your reference. Now, what do I mean by that? That means suppose you have taken a compound in a certain solvent which is a sample, the reference is typically the one which does not have the compound, that means it is only the solvent for you, right. So, what you do is, you can see here on this side, so look at the solution side, okay. So, look at this side, what you have is you have II and then you have IS. because you cannot measure I0 and I, you cannot measure that. You can only measure the, you only know the one which is incident and the one which is coming out, right. So, then what you do is this one goes to a detector and then you plot A or you calculate A based on log of I by Is. Okay. So, incident by what the sample sends through. Now, you do the same thing. What you do is now, see, you do not know what the incident light is, right. You do not know what the incident light is, because you do not know what incident light is being or is hitting the sample, because again of the simple reason that you have this wall. So, now what you do is the other half goes to the reference, which is the solvent only, no sample. There you get log of II over IR, right. So, the first one was I incident over I sample, the next one is I incident over I reference, no sample. Now, what would happen is, what would you do if you do AS minus AR, what would happen? What are you taking care of? Look at that. Do you have II anymore? You do not have I, it is already cancelled, right. So, this is what you call, you measure the absolute absorption spectrum. That means, by doing this dual beam, what you have done is you have taken II in both the cases, you have done a subtraction and that is cancelled out. So, what you are left with is the absolute or true absorption spectrum, which is referred to as IR over I of S. Okay. So, IR obviously would be higher because you do not have the sample. So, it is going to have higher intensity, and IS, where you have the sample, the intensity would be lower and you get the true absorbance. Okay. Now, how is the experiment typically done? Please also remember this is not the only thing. The thing is, if you are having two beams, that means you are using two cuvettes. So, this is cuvette 1, this is cuvette 2, right. Now, no matter how much carefully you manufacture the cuvettes, obviously you do not manufacture, but the company manufactures it for you, there would always be subtle differences in the cuvettes, always be subtle differences. So, what people would do then is, the first thing they would do is they would do a baseline. Baseline means in both the cases, that means in both the cuvettes, without putting sample, what would they put? They would put IR, that means R, reference. So, what would this take care of? This would take care of what? Whatever difference you have in terms of the cuvette path length, cuvette dimensions and all those things. The next one, so this is your baseline correction. So, the next one what you do is, now you put in, you take the IR in one of the cuvettes, I mean one of the sample holders out and put in IS, like you have done it. And then that is why when you will do your absorption spectroscopy, you would see there is something known as a baseline correction. This is exactly what you are doing. And the reason being that no matter how much you try, all cuvettes essentially are not the same, there are bound to be some differences. Okay? The differences might be small, might be big, depending upon how carefully the manufacturer manufactured it. Okay? So, this is the principle behind a double beam spectrophotometer, right. Now, you think about this, if you would do it with a single beam, you would not be having this luxury. Okay? That is why double beams are so very frequently used nowadays. So, this is just a block diagram of your absorption spectrophotometer. So, what happens is, you can see the two lamps, this is the tungsten lamp and this is the deuterium lamp, these are the two lamps out here. So, these by these two square things, right. After that, just let us not go into the specifics, just try to understand the scheme, the general scheme. Once the light comes out, the light has to be directed towards the sample. So, what does that, what is it done by? It is done by a mirror called a toroidal mirror. Okay. Do not worry about what a toroid is, the mirror is so chosen that you have the maximum amount of reflectance or the maximum amount of light which is guided towards the sample cell, that is what you pick out. Now, after that what happens is, you have an entrance slit, a slit which allows it to go through, you have a mirror out here, then you have a grating. So, this is a part of your monochromator. This is a part of your monochromator. Remember the monochromator we had in the previous slide. So, this is a part of the monochromator. So, the monochromator might be having one grading or two gradings, depending upon that it would be a single grading or double grading. So, this grading what it would do is, whatever light it is coming in, it would help disperse it. Okay, once it is dispersed, now you can see what happens is, again the light comes back, the parabolic mirror, this mirror which reflected the light onto the grading again collects it. Once it collects it, it comes through the exit slit like this. So, one was the entrance through which it went towards the parabolic mirror, went to the grading, came back to the parabolic mirror refocused it, it came through the exit slit. Now, once you have the exit slit, now look at this, your sample is here, right, this is your sample area. again you have to guide the beam or the light towards the sample area. So, what you have is after this exit slit you have another mirror. So, this is the direction. So, comes here, there is a toroid mirror, you have all of other optics, but finally see what happens, you have a reference beam and you have a sample beam. So, 2 beams are coming out, okay. And then again you have out here and then you have a detector, okay. So, either you have 2 detectors. 2 detectors means one for the reference and one for the sample, that means you have 2 beams, or you can have 1 detector and then do something so that you can get the proper absorbance, right. So, this is typically how the inside of an absorption spectrophotometer looks, a double beam one, right. Depending upon who manufactures it, components would differ, the type of mirrors would differ, the way you design the monochromators would differ, but the principle still remains the same. You are going to have this thing in general, okay. So, that's typically all what I had to tell you about absorbance. Just one thing I need to point out, which I forgot last time before I go on to fluorescence, is this. So, there is something known as oscillator strength. So, there is something known as oscillator strength. Now, where does this name oscillator come from? So, think about this. See, what was the intrinsic meaning behind an extinction coefficient? The intrinsic meaning behind extinction coefficient is what is the probability of that molecule absorbing light at that wavelength. Okay, that was the meaning of the extinction coefficient. It is so intrinsic to the molecule. It is a fundamental property of the molecule. Okay. Now, how does it happen? When electromagnetic light comes in, that is your energy density comes in, it is varying as a function of time, either cosine or sine. Now, what it does is when it hits your sample, it also sets the sample in motion. Now, it does not set the sample in motion. What does it set set motion into? It sets the electrons into motion, right, because that is the ones which are easily moved around. Now, the electrons would also respond to this oscillating nature of light. So, what would happen is these electrons would oscillate. Because electrons would oscillate, there would be change in charge distribution, all these things. So, remember this would bring about a change in your transition, in a change in a moment, giving rise to transition. So, we talked about the transition moment. So, the bottom line is that whenever your light comes in, it sends your electrons in motion. Now, depending upon the frequency, if the frequency is high, then the electrons would also oscillate with a rapid frequency. If the frequency is low, then the electrons would be oscillating less frequently. Okay? But so what it means is the mere extent of this oscillation of electrons will determine to what extent it absorbs at that wavelength, and hence this oscillator strength should be related. This oscillator strength should be related to your molar extinction coefficient in some way or the other. There has to be a relation, because both of these are speaking about the same thing. One is talking about the probability of the transition, the other one is talking about the oscillation of the electrons which finally lead to the transition. So, those typically these should be related. So, what happens is, so this is I will just give you the relation. The oscillator strength, it is symbolized by this thing F. Okay. So, F, the oscillator strength, is equal to, I will just give you the value, just remember it, 4.32 times 10 to the power minus 9 over n. N is a refractive index, remember, this is a refractive index, times this, times this. Okay. So, what it means is, so again n is a refractive index of your solution. Okay. And what do you have in the integral? What you have in the integral is here, just look at this. You have, what is epsilon? Epsilon is extinction coefficient. Epsilon is extinction coefficient, but what units are you expressing it in? Nu bar. You are expressing it in nu bar, that means centimeter inverse, right, times d nu bar. So, this essentially is your whole absorption spectrum, if you keep in mind. This essentially is the area under your whole absorption spectrum. Now, this is how an oscillator strength is related to epsilon, okay, just by this equation. Just keep this in mind, because both of these are talking about the same thing, right. The reason we choose nu bar, well, there are other reasons for it, but it is essentially because nu bar is proportional to energy, right, and you are supplying it with some energy density, and according to that your electrons are oscillating with that, whatever frequency you are supplying. Okay. Now, again this is based on the electromagnetic nature of light, this is based on classical physics, right. What about when we are talking about quantum mechanics? When we talked about quantum mechanics, we did an integral. What was that integral? That integral was the transition moment integral. Remember, we talked about the transition moment. So that was purely from quantum mechanics, right? We talked about wave functions and all these things. We talked about overlap, the Frank-Quantum overlap, and all these things. So see, if this oscillator strength is related to extinction coefficient, which talks about probability of transition, your transition moment also talks about your probability of transition, then again both of these things should be related, right? Because again both of these are talking about the same thing, right? Why should they not be related? Only one thing is, the one is classical, the other one is quantum. That's it. That's the only difference. So again, so there is a relation for us. So if just for the sake of knowing it, F is related to, I will give you m h nu over pi e squared times b 1 2, let this be 2, where m is the mass of the electron, m is the mass of the electron, nu is the corresponding frequency, and E you know is electronic charge, right. Do you remember what B12 is? Where did we encounter B12? Einstein's coefficient, right. Einstein's coefficient of absorption, this is the Einstein coefficient of absorption, B12. Okay. So this is what it should be related to, because you are talking about absorption transition. Now B12 is related by k times m squared, where k is a constant. Do not worry what the constant is. What is m? The m was the transition moment we talked about. So b is proportional to the square of the transition moment integral of the transition moment. F has a relation with b. B is proportional to m squared. That means F is also proportional to what? M squared. So this is the relation between the oscillator strength and the transition moment. Okay. So again it just says is that the probability of the electrons oscillating, determines the transition, and because it is a transition, I better have a relation between this oscillator strength and the transition moment integral. That is what we looked at just now. Okay. Do not worry about what the constants are and all these things. We do not have time to go into those details in this course at least, but this is the general expression or the general feeling you should be having about these two things. One is the oscillator strength and the other one is the transition moment. Both of these talk about the same thing. Okay. Good. So that was the last bit of information I want to tell you about absorption. So now, if you have excited the molecule, that means the molecule is, has absorbed light, the electrons have gone to the excited state, but it cannot stay there forever, right. They have to come down. That means they have to get deactivated or de-excited. So you go there, it stays there for some time, depending upon a host of other factors which we will talk about, and then after some time it will come down to the ground state again. That means it will relax or it will de-excite from the excited state. Okay. So what are the processes involved? Obviously one of the processes involved is fluorescence, right. So but let us look at a very important diagram. I am sure you have heard about this. This is called a Jablonski diagram. Okay. Now look, it has too many levels, energy levels, but do not be intimidated by that. All of these things you have seen before. First look at it step by step. What is S0? S0 is the singlet ground state for you. Okay. What is S1? S1 is the excited singlet state for you, right. What is T1? T1 is a triplet state. Good. Now you look at all these levels, associated with S1. What are these levels? These are your vibration levels. Remember when we were drawing the diagram, we had those vibration levels, right. So similarly, any electronic state like S0, S1, T1 would be having its corresponding vibration levels. So whether you look at S0, whether you look at S1, whether you look at T1, you would be having those levels anyway out there. Okay. So that is why what you have is, in S1 you also have these levels, in T1 you have these levels, right, in T2 you have these levels. Okay. Now what are S2 and T2? So if S1 is the first singlet excited state, S2 is what? The second excited state, T2 is what? The second excited triplet state, right. Okay. Now you have done an absorption. So right, so this is your absorption, this is the absorption, right. So, absorption takes place very fast, very fast. What is the fastest time scale, or what is the approximate time scale it takes place in? The absorption takes place in about 10 to the power minus 10 to the minus 15 seconds. Okay. So, 10 to the minus 15 seconds, that is what you are looking at, absorption, 10 to the minus 15 seconds. Okay. Good. So, now remember, when we have made this transition, the nuclei have not responded. Only after making this transition do the nuclei start responding to this change process. Good. Now, suppose it is so let us say, suppose let us look at these bunch of arrows. So, you have gone to S1. Now, you can see, as we discussed last time, you are not going to have only one transition, right, because if you are having this transition from where V is equal to 0 state of S0, because the electron density goes like this, you are going to have a band of transitions, right, throughout that wave function, right. So, that is why you have these series of transitions to different vibration levels, this vibronic transitions. We have talked about this intensity before, but the deal is this, guys. The deal is that you look at this, say you look at this arrow. This arrow takes the molecule to the highest vibrationally excited state in S0 based on this diagram, right, because this is a representative diagram. Okay. Now, let me tell you this, there are two things that can happen. Either the molecule from here comes back straight to S0, by some way or the other, or instead from here it slowly first decays to the first vibration state of S1 itself and then comes down. So, let me tell you this again. Consider the fact that I have gone to the highest vibrationally excited state of S1, right. So, that means you are already in a higher vibrational energy in S1. There are two things that can happen. The molecule can relax straight from here, this higher level, to the ground state S0, or it can slowly lose its energy, not slowly, it can lose its energy, go to V is equal to 0 of S1 and then come down. There are two ways of doing it, right. Okay. Now, this line, this wiggly line I just drew is referred to as VR, which is referred to as vibrational relaxation. Okay. You will see it in the next slide. This vibration relaxation, it is called vibration relaxation simple because the relaxation is happening between what states? Vibrational states, right. What is the time scale, guys? The time scale of this relaxation is 10 to the minus 12 seconds. 10 to the minus 12 seconds is pretty fast. Okay. It is faster than the time the molecule will take to relax from this state to the ground state. So, you can imagine what will happen is, which one will precede now, because VR is much faster than this process. So, you will be having a vibration relaxation first and then it would come down to the ground state, because its time scale is just faster than the time it needs to come down to the ground state straight away. So, this is called a vibration relaxation. If you would ever look up these processes, you would see that there is another process known as IVR, which is called intramolecular vibration relaxation, and people who are especially doing gas phase spectroscopy are very interested in this. Okay. Well, that is essentially looking at, right. But remember, in gas phase I told you do not have too much of broadening as compared to condensed phase, because condensed phase you have too many molecules, too many interactions. Your gas phase you do not have that. So, that is why people can potentially look at those, but here it is very limited. Okay. Now, so one was vibration relaxation, right. So, that means you were having relaxation in the same vibration levels, or rather in the vibration levels of the same electronic state. I am not talking about relaxation in two different electronic states. Also, second is vibration relaxation is a non-radiative pathway. That means when a relaxation is happening, it is not giving out any photons. What is it doing? It is giving out energy. It is giving out this energy as the thermal energy. Where did we use this? Do you remember? Where did we use this relaxation before? Come on, one of you will have to tell me. Okay, good. Which part? That itself was huge. Which part? What was the last thing we discussed in kinetics? Okay, the second last thing. It was not the last thing. before optical trigger? Temperature jump. We discussed temperature jump. What did we say in temperature jump? You heat the solvent goes up to a vibrational excited state, it relaxes, it loses the energy, and that energy is picked up by what? The protein molecules. This is essentially what is happening. So that excess energy gets picked up by whatever molecules you have in the surroundings, right? So anyway, in this case it gives out the excess energy and goes to V is equal to 0 of that electronic state S1. Okay. Now look at this process. This IC, what is the full form of IC? Internal conversion. Where does internal conversion occur? Between which two states? Between two electronic states, right? Either S1 is 0 or either S2 S1. Okay. But look at this. If you look at the IC, the internal conversion, it is again a non-radiative pathway. Again a non-radiative pathway. See, whatever wiggly lines you have, these all refer to non-radiative pathways. Okay, that is the importance of the wiggly lines. Now this internal conversion, if you look at this, please keep this in mind. This internal conversion, when you are having this conversion from S1 to S0, you are not having the conversion from S1 to V is equal to 0 level of S0. Where are you having the conversion to? You are having the conversion to a higher vibration level of S0 itself, isn't it? See, how would the conversion happen? The conversion would only happen very easily if you would have isoenergetic energy levels. That means if you have these two, the molecule, the electron can be here, the electron can be here, it does not matter, because these are isoenergetic, there is no energetic bias. It is not, it is like a Boltzmann population, right? This is obviously they are of same energy, so they have equal probability of being here or here. Now what will happen is, you think about this, see this is S1, the V is equal to 0 state of S1, right? So this is the one. So this is the V is equal to 0 state of S1, okay, and this is S1, this is overlapping with the higher vibration state of S0. The moment this one relaxes to the high vibration state S0, you know that this VR is very fast. So the moment it happens, it will come down, that is what you see, to the lowest vibration state V0. Now this is how an internal conversion happens. So it is always, remember, it is always between isoenergetic levels. Isoenergetic levels means levels having the same energy. It is just not jumping from one energy level to the other. Okay, this picture you have to have in mind. Okay, so that means wherever IC happens, it would be like this. Similarly, you can also have IC from S2 to S1, right? Again, there you see the lowest vibration state of S2 is overlapping or is equienergetic with a higher vibration state of S1. It goes there and then it again comes down to V is equal to 0 of S1. Okay, so that was your internal conversion. But please remember the internal conversion, and I come to this in the next slide where it is written out there. The internal conversion is essentially happening between two states having the same what? Same multiplicity. That is very important. Internal conversion, that means internal conversion between two states having the same spin state, same multiplicity, right? Okay. Now what about the ISC? What is ISC? It is intersystem crossing. As the name suggests, it is intersystem. That means you are now moving from one system to the other. So what are the two systems here? The one is say S1 to T1. Again you see in this ISC what is happening is it is again an isoenergetic transition, right, or isoenergetic conversion. That means the V is equal to 0 level of S1 is overlapping or is equienergetic or isoenergetic with a higher vibrational state of T1. It goes there, then it comes down. Okay, so this is intersystem crossing. Now the question is intersystem crossing allowed or not? Just tell me, is intersystem crossing transition allowed or not? Why is it forbidden? So there is a change in spin multiplicity. Now if you are having a change, obviously it is forbidden, then why do you see it? I mean you should not be seeing it, right? Theoretically you should not be seeing it, but it does happen. Mixing. So there is mixing between the triplet and the singlet state. That means whatever triplet state you see or whatever singlet state you see, that psi is equal to a coefficient times psi singlet plus a coefficient times psi triplet. So hence what I can write out here is I can write that psi, because of this intersystem crossing, says A plus B psi 3. There is A and B are the coefficients. A is the coefficient of the wave function corresponding to the singlet state, B is the coefficient of the wave function corresponding to the triplet state. That means that wave function is a mix of two states, singlet and triplet. Now, to what extent this mixing happens would finally determine to what extent you have the intersystem crossing, but there is something which increases the mixing. There is a term which refers to this mixing or increases the mixing. What is that? The term ends, it is two words, the last word is coupling. What is the first word? Okay, just go beyond. The first one is spin. What is the other one? Yeah, so it is spin orbit coupling. I told you everything almost, right? It is no longer a question, I was giving the answer to my own question. Anyway, so it is a spin orbit coupling. It is the spin orbit coupling which determines this intersystem crossing. Okay, so you have to have spin orbit coupling, right? Okay, guys, do not write. I had this, I will even give you a handout, so don't worry about it, just listen. Now, because this is a fundamental picture of fluorescence, this you always have to keep in mind if you are doing fluorescence, right? Whatever intensity of fluorescence, whatever emission of fluorescence you see is governed by these processes, as simple as that. Now, two things, whatever we have talked about, ISC, IC, VR, right, these are all non-radiative processes. That means they do not come with emission of photons, right. So, what are the two radiative processes that are left for us? One is fluorescence, the other one is phosphorescence. So, fluorescence obviously is from S1 to S0 almost always, only there are a few cases where you can have fluorescence from S2 to S0, there are very few cases. Okay. So, one is fluorescence and then the other one which is from T1 to S0, right, remember, which is again spin forbidden, but it gives out light, it is referred to as phosphorescence. Okay. So, that means in the Jablonski diagram you have a combination of two types of processes, one process that gives out photons, the other process that does not give out photons, that means you do not see. But how would you see? It is like this. Suppose you are putting in 100 photons, that means a molecule is absorbing 100 photons, right. If all the, that means if you are pumping in 100 photons and if you have a detector, it is an ideal case, you also look at 100 photons, that means each and every photon that it absorbed, it gave out one fluorescence photon. So, that means its quantum yield, it is something known as quantum yield, is 1. So, for every absorbing photon it has one emitting photon, right. I am talking about fluorescence now, let us not go to phosphorescence. Okay. However, the moment you see that the number of photons emitted is far less, it cannot be greater than the number of photons absorbed, it is far less than the number of photons absorbed. What does it mean? That means the other photons which you could not see must have gone through what? The non-radiative channels. So, that means you have a combination between the radiative processes and the non-radiative processes, and that finally determines to what extent you are going to see emission. See, the only thing you see is emission, remember, but by seeing the extent of emission you know how much of radiative non-radiative process you have, essentially how much of non-radiative process you have. That is why this parameter called quantum yield is of such a huge importance in fluorescence, right. That is essentially what it says. The yield means it is like if you are doing a synthetic reaction, you always talk about the yield, right. In this case you are also doing a reaction, but a photochemical thing. So, it is essentially photophysical, you are not doing any chemistry. So, that means you hit it with photons, it goes to the higher state, it comes down to the ground state, right, and whatever number of photons it yields in terms of fluorescence will give you the quantum yield. Okay. So, this is typically how a Jablonski diagram, or the features of a Jablonski diagram, right. Is there anything that I missed? Let me check out. I do not think so, but anyway, we will see soon. So, as I said, what are the deactivation pathways? One is a radiative de-excitation, it involves fluorescence and phosphorescence. The other one is a non-radiative de-excitation, which involves vibration relaxation, internal conversion and intersystem crossing. Okay. And I said that vibration relaxation is very fast, about 10 to the minus 12 seconds, right. Okay. So, let us look at the characteristics times now. Absorption about 10 to the minus 15 seconds, vibration relaxation you can see 10 to the minus 12 to the minus 13 seconds, fluorescence, that is lifetime of the excited state, can vary from 10 to the minus 10 to 10 to the minus 7 seconds. So, you can see now even before fluorescence happens, that means it comes down, your vibration relaxation is much faster. So, remember I said that it always has to go to the V is equal to 0 state. Okay. Similarly, intersystem crossing, which is 10 to the minus 10 to the minus 6 seconds. Internal conversion is non-radiative, it is from one electronic state to the other electronic state of same multiplicity, it is still 10 to the minus 11 to 10 to the minus 9 seconds. So, your vibration relaxation is still faster than what? Internal conversion, right. And then you have the lifetime of the excited state, which is a triplet. The phosphorescence, it is typically much delayed, right. See, fluorescence is the order of nanoseconds, phosphorescence in the order of microseconds, whereas 10 to the minus is micro.
ISC is much faster than
ISC?
Much faster than IC.
Why is it so? It says 10 to the minus 8 to 10 to the minus 10 minus 10 to 10 to the minus 8, right. IC is 10 to the minus 11 to 10 to the minus 9. Which is faster?
ISC.
Where? You look at the range. Okay, good. You have not crossed systems, right? Anyway, so yeah, where was I? Why is phosphorescence so delayed? Again, it is spin forbidden. It takes time, so that's why it's so delayed. So that means you can understand only after fluorescence is over will phosphorescence happen, right? Good. So this is again a very similar diagram. The only thing different which is shown out here is the vibration relaxation. You can see it is now showing the vibration relaxation to the V is equal to 0 state in that specific electronic state. Okay. Right. So we talked about internal conversion. So as I said, it is an isoenergetic non-radiated transition between two electronic states having same spin multiplicity. In solution, this process is followed by a vibration relaxation to the lowest vibration level or the final electronic state, with the excess energy being dissipated to the surrounding medium thermally. Okay, now please notice this. In solution, that is essentially in condensed phase. See, vibration relaxation will depend upon a lot of things, but obviously one of the immediate things it will depend upon is its interaction with the surrounding solvent. When you go to gas phase again, then you would realize that you do not have any solvent molecules, and hence probably in that case you would be able to pick out some vibrational structure which you do not see in the solution phase, okay, especially from the higher vibrational states. And we talked about the characteristic time. So, the intersystem crossing, it is a non-radiative transition between two isoenergetic vibration levels belonging to electronic states of different spin multiplicities. For example, an excited molecule in the 0 vibrational level of the S1 state can move to the isoenergetic vibration level of the T1 triplet state. So, this word is again a key word, isoenergetic vibration level. Now, crossing between states with different spin multiplicity is forbidden, but still you observe it because there is something known as spin orbit coupling, which brings about mixing of the singlet and triplet states. As I wrote that equation down, it makes ISC or intersystem crossing feasible. Okay. Now, what are the things that enhance or increase spin orbit coupling? There is one thing which is known as heavy atom effect. Now, heavy atom effect, as it suggests, is being brought about by an atom which is heavy. Okay, that is why the name. So, what happens here is intersystem crossing is enhanced by heavy atom effect that describes the effects of heavy atoms on spin forbidden transitions. The heavy atom effect can show itself as the internal heavy atom effect, where the incorporation of a heavy atom in a molecule will enhance the S0 to T1 absorption due to spin orbit coupling. So, that means it goes from S0 to S1 and then it goes to T1. That is why it is S0 to T1 absorption. Okay. Why is it called internal? It is called internal because it is present in the molecule itself. That means it is a part of the molecule. You have not done anything externally to it. It is already a part of the molecule. Okay, and I will give examples very soon in the next table. So, as an example, one iodonaphthalene has a much stronger S0 to T1 absorption than one chloronaphthalene. So, both are naphthalene derivatives, right? One has chlorine, the other one has iodine. Which one is heavier? Iodine is heavier. So, where would you see a better T1 population? In case of iodonaphthalene, right. So, that is why this table is very informative. It is referred to as internal heavy atom effect. What it says is, you have the molecule, then the first column is your phi f, which is the fluorescence quantum yield. I will come to that later. I have kind of given you an idea, and the next obviously is the phosphorescence quantum yield. Now, see what happens. You take naphthalene, the fluorescence quantum yield is what, 0.55, the phosphorescence quantum yield is really low, 0.05, right. Now, you go to 1 chloronaphthalene. In 1 chloronaphthalene, what happens to the fluorescence quantum yield? It immediately decreases to 0.06. Accordingly, the phi p, which is the phosphorescence, is increased. Why? Because chlorine now is heavier than hydrogen. It has introduced that heavy atom effect, and it is enhanced intersystem crossing by spin orbit coupling. Okay. Now, obviously, you guys would be smart. You go to bromo. If you go to bromonaphthalene, what would happen? You see the phi f. It is really low, 0.002, almost non-existent, and then phi p is 0.55. And you go to iodonaphthalene, what happens? It is almost not there. There is almost no fluorescence, and essentially whatever you see is in terms of our delayed emission, which is phosphorescence in this case. Okay. So, this is your internal heavy atom effect, because you see internal being that it is a part of the molecule itself. So, then if one is internal heavy atom effect, then obviously the other one would be external, right. So, then the external heavy atom effect is seen when a heavy atom is incorporated in a solvent molecule. That means, if you take 1 chloronaphthalene, it has a much stronger S0 to T1 absorption in iodoethane as compared to ethanol, because in iodoethane you have that iodine moiety. So, this is external because it is not part of the molecule, but it is a part of the medium, which is the solvent. That is why it is external, right. So, this is the characteristic time scale for intersystem crossing. Okay. Now, so this is like the layout you saw for an absorption spectrometer, this is the layout for a fluorescence spectrometer, but let us just not go there. Let us do a quick derivation. Okay. So, let us talk about fluorescence a little bit. Okay. So, fluorescence can be observed under two conditions. One is photostationary, and the other one is, sorry, this is time resolved. So, this is your steady state measurement, which is equilibrium, and the other one is your response as a function of time. So, this one is response as a function of time. Okay. Now, let us first consider the time resolved case. Okay, just for the sake of discussion, let us first consider the time resolved case. Okay. So, in the time resolved case, so this is what is happening, right. So, what you have is, you have done an excitation, that means the sample has absorbed and a set of molecules have gone to the excited state. So, that means you have, if the molecule is A, 1 stands for singlet. So, you have 1 A star concentration of molecules in S1, right. So, I have sent it there. Now, this one can come down by generally two types of processes. What are the two types of processes? One is radiative and the other one is non-radiative, right. So, then I can have this, I will have this where I will be having this one would come to 1 A, and this would be, say I will say plus H nu. So, this would be K R, K radiative, and I write H nu because it is radiative, that means it is giving out photons, H nu. The other one again it is 1 A, but this is non-radiative. So, I write K N R, and I am not writing H nu anymore because it is non-radiative. So, N R stands for non-radiative. So, that means N R. So, N R stands for non-radiative, okay, and R stands for radiative. and obviously k are the respective rate constants, okay, that goes without saying. Now, if you have to try to devise an equation for the rate of its decay, okay, so this is how it is done. The way it is done is, if you remember your T jump, temperature induced laser induced temperature jump rather. So, what happens is, I said one thing, that you have to do the temperature jump very fast, boom, like this, and then the protein slowly relaxes. So, here also you understand you have to do this excitation very fast, okay, and then that means it must be much faster than the fluorescence lifetime, or the time it takes to come down, and then you follow its progress as a function of time. Okay. So, what you do is, you do a delta function excitation, that means this is done with a laser pulse. This is done with a laser pulse, okay, and do an excitation which is very fast, right. That is what it means by delta. That means its time width is very small, it is there, the laser pulse is there for a very small amount of time, it excites it, and then you observe the decay of the excited state, right. So, then what will happen is, what I can now essentially write is d of A star over d of t should be equal to what? Should be equal to k r plus k n r 1 A star, right. So, let this be 3. Okay. So, now what I can do is, this is your kinetics, regular kinetics. So, I have d of 1 A star over 1 A star is equal to minus k r plus k n r d of t. Okay. So, then what I can write is 1 A star is equal to, after integrating, 1 A star 0, that means this is the concentration of molecules you have in the excited state at t is equal to 0, that is the moment you have done the excitation, times e to the power minus k r plus k n r t. Okay. This is equation number 4, right. This is just an exponential decay, right. It is exponential decay because that is how you set it up, right. Now, what I can do now is, I can rewrite this equation as 1 A star is equal to 1 A star 0 e to the power minus t by tau, minus t by tau, let this be 5, where tau is equal to 1 by, what is tau equal to? 1 by k r plus k n r. Remember, when we did laser induced temperature jump, it was what? K 1 plus k minus 1, right. Here it is k r plus k n r. Okay. So, this tau, which is the fluorescent lifetime, so this is referred to as your fluorescence lifetime. It depends upon two things. What does it depend upon? It depends upon the rate constant of the radiated process plus the rate constant of the non-radiated process. Okay. So, that means when you are looking at a fluorescence, when you are looking at the fluorescence, you are obviously looking at fluorescence, but you are looking at a process which is dictated by two different processes. One is the radiative and the other one is the non-radiative. Okay. That is why I said that when you are looking, when this thing comes down, it does not come down just by one process, it comes down by two processes, broadly speaking, and to what extent one process would be more or less than the other would depend upon the type of the molecule, the environment, and a host of other factors. You know, that is what makes fluorescence so interesting. Now, but the problem is, if you are doing a lifetime, right, if you are doing a lifetime, remember, this is what you get, tau. So, tau is essentially the time it takes for the molecule to reach 1 by e of its original value. Okay. So, that means you have 1 by A star 0 to start with at t is equal to 0. So, this tau is an exponential relaxation, right. It tells this tau is the time it takes to reach 1 by e of the original value, which was 1 A star 0. You know, that is how your exponential lifetime is defined. right. Now, the problem is this guys, because we know that tau has both Kr and Knr, if I only make a measurement of tau, I would not be able to get these, right, because I have one measurement, but I have two variables which is Kr and Knr. Now, the same thing happened in laser induced temperature jump. What did we have? We had K1 plus K minus 1, but both of these were coming together, so we could not get that. So, what did we need in that case? For the temperature jump we needed equilibrium, right, because we had the K equilibrium. So, that means we had two equations, two unknowns. What would we do here? Obviously, one is tau, the other one which I just discussed with you is the other one is the quantum yield. The quantum yield is the fluorescence quantum yield phi f is given by Kr over Kr plus Knr. Okay. So, this is equation number 6. This is referred to as the fluorescence quantum yield. Okay. This is referred to as the fluorescence quantum yield, and once you have this fluorescence quantum yield, we have two equations. One is tau equal to 1 by Kr plus Knr, and phi f is equal to Kr over Kr plus Knr, right. You can use these two equations to get the two unknowns. Okay. Quantum yield calculation or measurement can be done separately, not an issue, people do it on a regular basis, right. So, essentially then the definition of quantum yield phi of f is equal to the number of photons emitted, over the number of photons absorbed. This is the definition of quantum yield. Okay. So, essentially it is a ratio, right, it is a ratio of what, the number of photons which actually come out as light, in this case fluorescence, over the number of photons it originally absorbed. So, that means if you have 100 photons, if it gives out 100 photons in the form of light, your phi f would be what, 1. If it gives out 50 photons, accordingly this phi f would be 0.5, okay, like that. Good. Okay, now, this was your time resolved. So, time resolved means you have excited a molecule, right, and then you are looking at its progress, that means its decay from the excited state to the ground state as a function of time, right. So, that is why there are like time resolved spectrophotometers, right, which do this job routinely for you. You have excite and then it comes down and you fit it to a certain routine, a certain form, certain functional form, and you extract your parameters, okay, tau and all these things. Now, we would not be discussing that at much length. However, I would just like to divert your attention to something which we do regularly, at least all of you do regularly, possibly on a regular basis, is steady state fluorescence, right. That means it is like an absorption spectrometer. Now you are having a fluorescence spectrometer and you are sticking your sample in to look at what the fluorescence spectrum is. Like you had an absorption spectrum for tryptophan, tyrosine, all these things, these should also be having their corresponding fluorescence spectra. So, just give me a little more time and we will be done with this. So, going back to the slides. So, this is a typical diagram or layout, optical layout of a fluorescence spectrometer. Now, see how similar it is to absorption, right, and what are the things it has. You have to have a source which excites your samples, because if the sample does not absorb, it will not go to the excited state, no fluorescence. So, you have a xenon lamp, right. Now, you have a xenon lamp in this case, but in case of absorbance you do not have a xenon lamp. It is not that you cannot have a xenon lamp, people can have xenon lamps, okay. Only that in that case you had two lamps, deuterium and tungsten, it's using a more common, right. See, after that what it does is, because you have to spread this out, it goes into a compartment which has the excitation monochromator. So, again you disperse your xenon lamp beam into its component wavelengths, okay. I will show you the xenon lamp spectrum. After that it comes out, like this, and you can see out here. So, this is the grading, I was telling you this is the part of the monochromator, this is the grading where it gets dispersed. Now, you can see out here so this is your slit, that means there is an opening out here which allows, by which you can determine how much of light you allow to pass through to hit the sample. So, if you would be doing, if any of you would have done steady state fluorescence, you would see that in the control panel or in the software you determine something known as slit width, whether it is 5 nanometer or 1 nanometer or 10 nanometer, this is essentially what it is. So, you can imagine one thing, if this is your beam of light having the total output coming in, if you open it you will be having the maximum intensity. Now, if you slowly close, what will happen? The amount of light that comes through and hits the sample decreases. Now, there is a reason you do it. One of the main reasons is some of the samples are very conducive to photo bleaching. That means, if you have too much of sample coming in or too much of light coming in, then that fluorescent molecule can actually get damaged, right, irreversibly damaged. So, you would want to stop that. There are also other things. Sometimes what happens is that your detector, whatever your detector is, has a certain response where it is linear to the number of photons that is coming in. If you shine too much light, then that means there would be too much fluorescence and it would cross that linear region, right. So, anyway, there are a host of other things, but the bottom line is, using the slits, what you can do is you can control the amount of light that is coming in and hitting your sample, right. Then obviously, you have your sample compartment out here, right. This is your sample compartment. Now, which I will not discuss with you, but I will just quickly tell you is, you see there is a beam spreader here. Remember the beam spreader we had in the absorption spectrometer. In this case, what it does is, here one is coming to the sample, a part of this light is going to an absorbance computing cell, so compensating cell, right. So, this one, this is called a reference sample, it goes to a reference photomultiplier tube. And the reason is this, to be very short, if you are doing a fluorescence experiment, say for 10 hours, that is the time you need. You started with a certain intensity of light before, say at 5 minutes you started with a certain intensity. Now, when you go to 500 minutes, there is no guarantee that the intensity you started with would be exactly the same as the intensity you have after 500 minutes. So, what you would see is, if you are doing a time consuming experiment, then because the intensity of the lamp has decayed as a function of time during that time interval, because it is a very long experiment, the fluorescence intensity would depend upon the excitation intensity. So, whatever decrease or increase you would be having would not be related to the sample, but would actually be an artifact of what? The light that you sent through. So, then what you do is this reference photomultiplier, you know what it does? What it does is it always normalizes with respect to your beam that is coming in. So, you take your actual sample and you divide it by the reference photomultiplier intensity. That means, that one actually tells you or actually normalizes whatever intensity you have, and you get the corrected or true, not true, the corrected fluorescence spectrum. So, that is what you should always use if you are doing it for a very long time, okay. Especially if you are doing like a thermal melt for a protein using fluorescence, it takes time, you better do this, okay. That is how you will get the absolute best signal or spectra, okay. So, after the sample compartment it comes out, you have a reflector out here. Now, this sample compartment again goes into an emission monochromator. So, the sample is emitting, it emits light over a range of wavelengths, like it absorbs over a range of wavelengths, it emits over a range of wavelengths. So, to look at what wavelengths are, you have to disperse the wavelengths, you disperse it with the help of a grating, and after that it comes to the PMT and you record your spectrum, okay. So, this again is just a typical layout of your fluorescence spectrometer. See, there is nothing big about it. Yeah, obviously putting these things together, the company does it for us, so we do it, right. We do not have to worry about this, but if you look at each and every component, you would understand that trying to figure out why each and every component is there is not a big deal, because you know why each and every component is there. It is not something we can never think of. We know why a monochromator is, we know why a slit is there, we know now, at least we know to a certain extent why the reference photomultiplier tube is there. So, all these things we can logically think. If you would ever think about this while you are doing an experiment, you would see that experiment for you becomes a lot better, because you understand it a lot better now. You have a personal feel about that experiment, and that is why it is so essential for you guys to know what is there inside the box you are using, without just treating it as a box, okay. So, that is why I am taking this pain to show you the optical layout, which means it is not, it is nothing out of the ordinary, it is just some very ordinary components you put together, right. Obviously, expertise comes in terms of manufacturing these things and all, right, and then you put together in terms of fluorometer, and here this is a fluorimeter that people typically use out here. So, you can see this is, this you have taken the top of a fluorimeter, right. This is no longer a block diagram, right. This is a fluorimeter for you. Okay. Now, see what happens. This is the xenon lamp source, right. You can see this is a lamp out here, right. Then there is a lamp. So, this is a monochromator. So, it should be A out here. So, monochromator comes here. Here is a monochromator out here, right. From the monochromator, you can see this brown thing kind of gives you the path, yellowish brown thing gives you the path of the excitation light. So, it is from the lamp, it goes here, there are mirrors, monochromator comes through. You can see this is the excitation slit, and this is your sample compartment. Can you see this is your sample compartment, right. This is sample compartment. Okay. Now, after the sample compartment, what happens is the sample emits light. So, this is your fluorescence, right. This you are looking at, it fluorescence comes out, you can see you have a detector out here, right. You have another monochromator, which is the emission monochromator I showed you out there. Then you have the detector, and it detects the light for you. Okay. So, just think about this based on the block diagram, you understood what is there inside. Okay. There is nothing big, it is just components put together, so that you can collect a spectrum. Okay. And finally, this is your xenon arc lamp spectrum. Why did I use that? You can see this is how the spectrum goes. It goes from about, this is 250 nanometers on the x axis, and it goes to pretty high, as 1.1 or 1.2 micron. Now, you can understand why, if I would be using a UV visible spectrophotometer and I would not be taking a xenon lamp. Can you tell me now why? I would rather use a deuterium lamp than a xenon lamp. Why? When I am doing a UV visible experiment, UV, I would rather try to start from 200, right. Now, at 200, if I am going to look at an absorbance, your proteins typically have a backbone absorbance at about 222. Okay, let me tell you that. So, if I would be trying to look at a protein absorbance at 222, would I ever get that with a xenon lamp? Why not? Because you look at the intensity of the xenon lamp, what happens? At 250, it is gone. After that, there is nothing else from the xenon lamp. But if you would use a deuterium lamp, the deuterium lamp you will see would kind of go very high up. So, that is why you would use a deuterium lamp rather than a xenon lamp in an absorption spectrophotometer. But it is not that people do not use it. If you want to go to 250 and above, no problem, use that xenon lamp. Okay. So, and if some of you have ever done this fluorescence experiment, you would see that there is an instrument calibration that goes on. The instrument, that fluorimeter, it calibrates itself according to this region of the xenon lamp. Okay. And this is how a xenon lamp typically looks. Okay. Now, this is a personal request from my side, do not take the cover off and look at a xenon lamp, because that might be the last time that you look at anything, right. The reason is these are depending upon the power, depending on the wattage, these are very high luminosity, these are very high intensities. Even before you realize, it will damage your eyes. Okay, you would never want to do that, right. And these also have very high voltages going across them. So, you can see what happens is, that is why it is not just exposed like that, it is housed in a typical housing. What the housing has is, you forget these condensers, reflect adjustments and all these things. You look at this, the fan, like when you guys get heated up, you need a fan to cool yourself down. The same thing happens with the xenon lamp, right. So, it is not only we that need fans, it is also these instruments that need fans. So, xenon lamp, because it is giving out so much of light, that housing typically gets very warm. So, if you would ever look at the fluorimeter at a place where you have the xenon lamp, you will see there is a fan running all the time, it cools it. Okay. If you do not have that fan running, you would never, if you see that the fan is not running, never put your instrument on, because it will damage your instrument. Okay. Well, these are the functions of the arc lamp. As I just said, I will just complete it. The gas in xenon lamps is under high pressure, about 10 atmospheres, and explosion is always a danger. The housing protects the user from the lamp and also from its intense optical output. The housing also directs air over the lamp and removes excess heat and ozone. It also removes ozone. Okay. So, again this is a xenon arc lamp, and the caution with which we end the class is, a xenon lamp that is on should never be observed directly. The extreme brightness will damage the retina, and the ultraviolet light can even damage your cornea. Okay? So, you have to be careful. See, you just do not go and open up an instrument. At least first you know what I should be doing, what I should not be doing. There are many, each and every instrument comes along with a manual. It is called a manual, right. It tells you how you should be doing things, how you should not be doing things. Instead of how you should be doing things, sometimes take a look at how you should not be doing things, right. That will sometimes help you really. That is a short thing, that is a small thing, much smaller than what you should be doing, but that is where you should start, and at least that is the first thing you should keep in mind before trying to do what things you should be doing. Okay.